So this is the Chapter 6 video for this Chapter 6 test review. This is the third and fourth page. A gardener is growing a lily plant and starts with 4 lilies. The number, 4 lily pads. The number of lily pads increases at a rate of 6.5% per day. Letter A, write an equation for the number of lily pads L the plant has. L is the number of pads. My initial value is 4. 1 plus my rate. My rate is 6.5%, so that's 0.065 to the t power. But 1 plus 0.0625, is 1.065 to the t power. Right? Letter B, on about what day will the plant have 9 lily pads? So I go to y equals, I plug in my equation, 4 times 1.065, that's not a 1, to the x power. I can go to my table. I want 9. On the 12th day, I'm not there yet. On the 13th day, I've got 9. So it's on the 13th day. Okay. How many pads will the plant have on the 20th? So I go to my calculator. I want the 20th day. So I go down to where x is 20. 14.095. So that's 14 pads. Okay. Number 4. In the year 2000, there were 54 members in an after-school athletic club. Membership declined at a rate of 5% per year from the year 2000 to 2007. Write an equation for the number of members M in the after-school athletic club. So M is the number of members. My initial value is 54. I am losing members. So that's 1 minus 0.05 to the t power. However, 1 minus 0.05 is 0.95 to the t power. So that's per year. Okay. In what year did the club have less than 40 members? So I want 40 members. I want M to be 40. So I go back to y equals. I plug in my equation. I don't need the 0. 54 times 0.95 to the x power. I want it to be 40, so I could make y2 40, or I could look in the table. My window for 40, well, 54 was the total amount. I don't need to go to 305. I could go to 60 and get that. I probably am not going to have 45 years, so let's go ahead and go to 15 years. If I can see the intersection, I can find it. Second trace. Number 5, it's intersection. Enter 3 times. So 5.85, so that's about 6 years. Since I started in 2000, 2000 plus 6 is the year 2006. How many members were in the club in the year 2007? The year 2007 is 7 years from when I started. So I'm going to go to the table. 7 years would be 37.7. So about 38 people, about 38 members. Compound interest. Annually, more often, and continuously. Write an equation and solve the following problem. Allison invested $1,000 at 6% compounded weekly. How much will she have in the account in 7 years? Compounded weekly is more often. So y is equal to my initial amount times 1 plus my rate, 0.06, divided by weekly is 52 weeks in a year, to the 52 times 7. Pull up my handy dandy calculator. So I need 1,000, my initial amount, times 1 plus 0.06, my 6%, divided by my 52 weeks in a year, to the, don't forget to open up a second set of parentheses, 52 times 7 years, and I get $1,521.59. $1,521.59. Number 2, Chad invested $5,000 at 7% compounded monthly. How much will he have in the account in 10 years? So again, my initial amount is $5,000. 1 plus, my rate is 0.075. That's 7% as a decimal. Compounded monthly is 12 months. To the 12 times 10, since it's over 10 years. Bring up my handy dandy calculator. Do the same thing. Start off with $5,000. 1 plus 0.075. Divide by my number of years, 12 years. To the, don't forget to open a new set of parentheses, 12 times 10. And I get $10,560.32. $10,560.32. Number 3, Melissa invested $10,000 at 12% compounded quarterly. How much will she have in the account in 5 years? Again, Y is equal to my initial investment, my principal, 1 plus my rate, my rate as a decimal is 0.12 divided by 4 since it's quarterly, to the 4 times 5 since it's 5 years power. Bring up my handy dandy calculator, and I can go ahead and plug in my $10,000 times 1 plus 0.12 divide by 4, which is quarterly, to the, don't forget to open up a new parentheses, 4 times 5, which is 20, and I get $18,061.11. $18,061.11. Number 4, Michael invested $500 compound at 8.25% compounded continuously. How much will he have in the account in 20 years? All right, so we're going to go Y equals. This is continuously, so I'm going to use PERT, P times E to the RT. So Y equals my original amount, $500, times, I don't need the parentheses, so let me start that over. $500 times E to the power of my rate, 0.0825, that's 8.25 as a decimal, times my number of years, 20 years. And all of that is in my exponent. So again, I bring up my calculator. I plug in my initial amount. E is to hit second. ln gives me e to an exponent, 0.0825 times 20 years gives me $2,603.49. $2,603.49. Number 5, Leah invested $800 in a savings account at 8% compounded daily. How long should she leave the money in the account if she needs $1,000? So this is a little bit different. I want to start off with $1,000. That's the amount of money I want. I started out with $800. This is 1 plus my rate, 0.08. Divide by daily is 365 days, to the 365 times T, which is what's missing. I don't know how long I want to invest this. That's what I want to find. How long should she leave the money in? So I pull up my handy dandy calculator. Since I have a starting amount and an ending amount, I'm going to go to my Y1, plug in my first equation, 800 times 1 plus 0.08 divided by 365 to the 365x. And it's x that I want to find. How long? My Y2, I'm going to plug in that $1,000. Now that means I need to see 1,000 in my Y window. So my Y window needs to go above 1,000. I'm going to make it 1,200. I'm not sure how many years. 20, 15 might have worked. I'm going to try 20 years to see what that would look like. I'm going to hit graph. There's one graph. There's the other. If I can see the intersection, I can find the intersection. Second trace to number 5 is intersection. Hit enter 3 times. 2.7896 years. So 2.79 years. 2.79 years. If I needed just the number of years, I would round that up to 3 years, but 2.79 years is how many years she would need to leave it so she can have her $1,000. Riley needs $20,000 to put down on a new condominium. Her investment company predicts that she can invest her money with them and increase her investment by 12% annually. She wants to purchase the condominium in 5 years. How much should she invest now? So again, this is that same style of problem. I want to end up with $20,000. I don't know how much money I'm starting with, but I'm going to get 12% annually for 5 years. I want to solve for P. Again, I go to my calculator. I go to Y equals. My first equation is x, the amount to start with, times 1 plus 0.12. Since it's annually, there's no compounding through the year. I can just put 1.12 to the 5th power. And I want this to be $20,000. Now here's the thing. X is not an exponent. X is not an exponent. It's just the principal. That means my X and my Y have to be large numbers. So $20,000 is the amount of money I want to have. So I'm going to go to 22,000 for my X and my Y. So it's too large. I'm going to graph. I see my intersection, so I can find my intersection. Since x is not the exponent, this actually turns out just to be a line, since x is just my principal. Second trace to go to my calc menu. Number 5 is intersection. Hit enter 3 times. $11,348.54. 348. $11,348.54 would get me $20,000. So now to number 7. Katie invested $2,000 at 6.5% compounded continuously. How many years would it take for her to investment to double? Doubling means I need $4,000 when I started with $2,000. Compounding continuously is e to the rate. 6.5% is 0.065 times the number of years. I don't know. I'm going to call it x. Again, I pull up my calculator. My equation is 2,000. I'm going to do that up here. 2,000 is my starting amount. I want this times E, since it's compounding continuously. My rate is 0.065 times X. And I want it to be $4,000. My x is in my exponent, so my x doesn't have to be anywhere near as large. I'm going to guess 50 years. I want to get up to $4,000, so I just need a little over that. So I'm going to go 5,000. There's one graph. There's the other. If I can see it, I can find it. Second trace to go to the calc menu, number 5. Enter, enter, enter. 10.66 years. 10.66 years. All right, let's go to the next page, last page. Properties of logarithmic functions. Simplify each of the following, condense as a single logarithm. Leave your answers in log form without an exponent, okay? If I'm adding two logs, that means I want to multiply their arguments. So this is log of 20. I'm adding two logs, so I multiply their arguments. 4 times 3.5 is 14. That's an ugly 4. So this is log of 14. Subtracting means I divide the arguments. So log of 60 divided by 20 is log of 3. Remember, none of these have a base. So all of these are base 10, the common log. So I just write log. Whenever I subtract, I divide. 63 divided by 9 is 7. On this last one, I have an exponent, which tells me I want to bring it to the front. 5 log base 10 of 4. Number 2, write each of these in exponential form. So I'm starting with the log, so my base stays the same. My answer becomes my exponent. My argument becomes my answer. 6 to the x is equal to y. My base stays the same. My answer becomes my exponent. My argument becomes my answer. 4 to the x is equal to y. My base is 10. My base stays the same. My answer becomes my exponent. My argument becomes my answer. 10 to the y is equal to 7. My base stays the same. 5. My answer becomes my exponent. My argument becomes my answer. 5 to the y is equal to x. And lastly, natural log, remember that is log base e of 9 is equal to the x. Again, my base stays the same. E, my answer becomes my exponent. My argument becomes my answer. E to the x is equal to 9. Now I want to go the other way, write each of these in logarithmic form. Now that I have an exponent, I want to write it as a log. So I start by writing log of, my base stays the same. My answer becomes my argument. My exponent becomes my answer. Log base 6 of y is equal to x. Again, log, my base stays the same. My answer becomes my argument. My exponent becomes my answer. Log base 7 of x is equal to y. Again, log, my base stays the same. My answer becomes my argument. My exponent becomes my answer. Log base 2 of 16 is equal to 4. Again, log, my base stays the same, 6. My answer becomes my argument. My exponent becomes my answer. Log base 6 of y equals 4x. Lastly, log, my base stays the same, 9. My answer becomes my argument. My exponent becomes my answer. Log base 9 of y is equal to 3x. Number 4, find the value of each of these logarithms. Remember, a log is an exponent. You could plug this into your calculator if you know what you're doing. The way I've taught you to do it is let it equal to x. So change from a log to an exponent. 4 to the x is equal to 64. That means 4 to the x is equal to 64 is 4 to the third power. So x is equal to 3. Next one, again, let it equal to x. 10 to the x is equal to 1,000. Okay, well, 1,000, that's changing from a log to an exponent. 1,000 is 10 to the third power, so x is equal to 3. Next one, set this equal to x. 2 to the x is equal to 32. 32 is 2 to the 5th power, so x is equal to 5. And letter D, again, set it equal to x. 7, change it to an exponent. 7 to the x is equal to 2,401. 2,401 is 7 to the 4th power, so x is equal to 4. If the bases are the same, the exponents have to be the same. That's what I'm doing on all of these, getting the bases to be the same. Let it equal x. 5 to the x is equal to 125. Change it from a log to an exponent. 125 is 5 to the 3rd. The bases are the same, so my exponents are the same. Number 5, simplify each of the following and find the value of these logarithms. So I want to do the same idea. Log base 2 of 8 plus log base 2 of 8 is log base 2 of 8 times 8. Whenever I add, I multiply is 64. Let that equal x. 2 to the x is equal to 64 is my exponent because the bases stay the same. The answer becomes the exponent. The argument becomes the answer. 64 is 2 to the 4th power, 2 to the 6th power. So x is equal to 6. Next one, whenever I subtract, that means I want to divide. So log base 2 of 32 divided by 8 is 4. Again, set that equal to x. 2 to the x is equal to 4. Well, 4 is 2 to the 2nd power. My bases are the same, so my exponents have to be the same. X is equal to 2. And lastly, I'm dividing here. So we say log base 5 of 500 divided by 4 is 500 divided by 4 is 125. Again, I want to solve this I want to simplify, find the solution. So I say it's equal to x, change the log to an exponent. 5 to the x is equal to 125. 125 is 5 to the 3rd power. My bases are the same, so my exponents have to be the same. X is equal to 3. Solving logarithmic and exponential equations. Okay. So here we go. Log base 4 of x equals 64. So the first thing you want to do is the base stays the same. Change it to an exponent. The answer becomes the exponent. The argument becomes the answer. 4 to the 6th power is x. So x is equal to 4,096. Plug that into your calculator. Letter B. I have logs on both sides. There is not a base written for either one. That means it's base 10. But since I have log base 10 on both sides, since the logs are the same, the bases are the same, my arguments have to be the same. So I divide both, so 10x is equal to 200, so x has to equal 20. Number or letter C, when I add 2 logs, it's the same as if I was multiplying their arguments. Excuse me, that's a mistake. So this is log base 2 of 72. My bases are the same, my logs are the same, so my arguments have to be the same. So I can say that 8x is equal to 72, so x is equal to 9. Letter D, whenever I subtract, means I divide the arguments. Log base 3 of x divided by 6 is equal to 2. I have logs on one side, so I change it to an exponent. My base stays the same, 3. My answer becomes my exponent. My argument becomes my answer. To solve for x, well, 3 squared is 9. I multiply both sides by 6. So 9 times 6 is 54 is equal to x. And lastly, whenever I add, that means I multiply my argument. So log of 6, log base 6 of 4x is equal to 2. I have log on one side, so that means I'm going to change this to an exponent. 6 squared is equal to 4x. 6 squared is 36. 36 is equal to 4x. Divide both sides by 4. X is equal to 9. Solve each of these for x. Run to the nearest thousandths place. I want to get the x out of the exponent, so I'm going to change it to a log. Log base 10 of 4 to the x is equal to log base 10 of 8. Bring the x to the front, just like my property tells me I can do. X times log of 4 is equal to log of 8. Divide both sides by log of 4. X is equal to log of 8 divided by log of 4. I go to my handy dandy calculator. I do log of 8, close parentheses, divide by log of 4, close parentheses, and I get 1.5. Okay. Letter B, I want to do the same idea. I want to get the x out of the exponent, so I'm going to take log of both sides. Log of 6 to the x is equal to log of 40. Bring the x to the front. I get x. Log of 6 is equal to log of 40. Divide both sides by log of 6 to get the x by itself. X is equal to log of 40 divided by log of 6. Bring up my handy dandy calculator. Log of 40 divided by log of 6. I get 2.0588. So I am going to say x is equal to 2.059. Letter C, I'm running out of space here. Again, I want to take logs of both sides. Log base 2 of, excuse me. Log of 2 to the 3x is equal to log of 22. Take logs of both sides. Bring the 3x to the front. 3x log of 2 is equal to log of 22. I want to divide both sides by log of 2, so I get 3x is equal to log of 22. That's not right. 3x is equal to log of 22 divided by log of 2. I go to my handy dandy calculator. I say log of 22 divided by log of 2. I get 4.459, but that's 3x. So 4.459. So 3x is 4.4 ... Divide both sides by 3, and I get x to be, so I want to divide by 3 to get x by itself, 1.486. 1.486. Number 4, letter D here, I obviously don't have enough room. I tried to make it fit, but well, actually, I tell you what. Let's see if I can do it right in this space right here. I'm going to do 3 to the x minus 6 is equal to 28. Add 6 to both sides. You get 3 to the x is equal to 34. I'm going to do log of both sides. So log of 3 to the x is equal to log of 34. Bring the x to the front. So I'm going to get x. log of 3 is equal to log of 34. Divide by that log of 3. So you get x equals log of 34 divided by log of 3. Pull up my handy dandy calculator. I do log of 34 divided by log of 3. And I get 3.2098, so it's 3.210. 3.210. That's the answer to letter D way up there. All right. Last set of problem, application of logs. Application of logs. One of Charles Richter's formulas relates the amount of energy released by an earthquake to its Richter magnitude. Log E, so log base 10 of E equals 11.8 plus 1.5 times M. Solve Richter's formulas for E in terms of 10. As we did before, this is base 10. So change it to an exponent. 10 to the 11.8 plus 1.5 M is equal to the amount of energy E. Use the formula at number 1 to find the energy produced for the following. A magnitude 4 small atomic bomb. So this is 10 to the 11.8 plus 1.5 times 4. Bring up your calculator. And we do 10 to the 11.8 plus 1.5 times 4. You don't need parentheses in there. I guess I should just say this is 1.5 times 4. Hit enter, and it's 6.3095. So that's 6.310 times 10. My exponent was to the 17th power. Now I want to do the same thing, but for the San Francisco earthquake of a magnitude 8. So I bring up my calculator. I'm going to hit second enter to bring up my last answer. Instead of a 4, I'm going to do magnitude 8. And I'm going to get 6.3095 times 10 to the 23rd. So again, it's 6.310 times 10 to the 23rd power. And lastly, how much more energy was produced by the San Francisco earthquake as opposed to the small atomic bomb? I want to take the earthquake and divide by the bomb. So you're going to go 6.310. Now, honestly, it is best if I put those in parentheses. Times 10 to the, well, this was the 23rd power. That's the San Francisco earthquake. And I want to divide by 6.310 times 10. Again, I won't need that in parentheses. To the small atomic bomb was to the 17th power. And I get 1,000,000 times more powerful. 1,000,000 times more powerful. That is my review. Good luck on your test.